Hello everyone, welcome back to my channel. In this video, I'm going to explain about transist analysis of first and second order circuits. So coming to the details of this topic, we have introduction, transist response of RL-RC series and RLC circuits for DC excitations, and initial conditions. So first, let us know the details introduction of this topic. So in this topic, we shall study transist response of RL-RC series and as well as RLC circuits with external DC excitations. So these transients are generated in electrical circuits due to abrupt changes in the operating conditions when energy storage elements like inductor or capacitor are present. So these transient response is the dynamic response during the initial phase before the steady state response is achieved when such abrupt changes are applied. So to obtain this transient response of such circuits, we have to solve the differential equations, which are governing equations representing the electrical behavior of the circuit. Okay, a circuit having a single energy storage element, for example, either capacitor or an inductor, is called as a single order circuit, and its governing equation is called a first order differential equation. Okay, a circuit having both inductor and capacitor is called a second order circuit, and its governing equation is called a second order differential equation. So the variables of these differential equations are currents and voltages in the circuit function of time. So coming to the next topic, we have the transient response of RLRC. So here now I'm going to explain only about the transient response of RL with the DC external DC excitation. As you can see, this is the circuit diagram for the RL circuit with external DC excitation. So here we have a simple RL network subjected with a DC excitation circuit. So this circuit consists of a battery whose voltage V is in series with a switch and a resistor R and an inductor L. So the switch is closed at the time t is equal to 0. So when the switch is closed, current tries to change in the inductor, and hence the voltage VL of T is induced across the terminals of the inductor in opposition to the applied voltage. So the rate of change of current decreases with the time, which allows current to build up to its maximum value. Okay, so now we have to apply the Kirchhoff's voltage law for the circuit. So when we apply the Kirchhoff voltage law, we have the equation as V is equal to V of R, VR of T plus VL of T, as well as we have to apply the same Kirchhoff voltage law to the current. So we have the current equation will be I of T is equal to 0 for T is less than 0. And using the standard relationships of voltage and current for the resistors and inductors, we can rewrite this equation as so this V is equal to V is equal to V is equal to Ri plus L di by dt for t is less than for t is greater than 0. And one direct method for solving such differential equations consists of writing the equation in such a way that the variables are separated and then integrating each side of the equation. So the variables in the above equation I and t. This equation is multiplied by dt and arranged with the variables separated as here. So here we have the equation Ri into dt plus LDI is equal to V into dt. Further we multiply this, we will have the equation of LDI by V minus Ri is equal to dt. We have this equation. So next we have to integrate it directly so that we will get the equation as minus L by R into In into V minus Ra is equal to T plus K. So here where K is the integration constant. So in order to evaluate K, an initial condition must be evoked. So we have to take T is equal to 0 where I of T is equal to where I of T is 0, and then we have I of 0 minus will be also 0, since the current in the inductor cannot change by a finite amount in 0 time, without being associated with an infinite voltage, so that we have I of 0 plus is equal to 0. By setting I is equal to 0 at t is equal to 0 in this equation, we have minus L by R into In of V is equal to K. By further classified, we have the equation as minus L by R into In into V minus Ri minus In into V is equal to T. So by rearranging this equation, we will have this equation In into V minus Ri by V is equal to minus R by RL by T. We have this equation. By taking algorithms on both sides, we will have the equation as V minus Ri into V minus Ri by V is equal to e to the power of minus RT by L. So then we have which we can see that we have I of t is equal to V by R minus V by R into E minus RT by L for t is less than 0. So thus an expression for the response valid for all time where t would be where t would be I of t is equal to V by R into 1 minus e to the power minus RT by L. So further we can normally written this equation as I of t is equal to V by R into 1 minus e to the power minus t by tau, where here tau is called as a time constant of the circuit and its units will be in second. So now let us see the voltage across the resistance and the indicator. So here we have the voltage across the resistance and the indicator where time is less than 0. It can be written as uh, in this equation V of R is equal to VR of t is equal to I of t into R is equal to V of 1 minus e to the power minus t by tau. So we have the same expression for the inductor also by given here. So we have both plots for the current and the voltages for this transient series of RL circuit as shown here. So these are the two plots for the current. So first plot is for the current and the second plot is for the voltage. So here the tau, so at t, tau the voltage across the indicator will be as for inductor, the voltage across the inductor will be as given in this equation and the voltage across for the resistors will be given in this equation. By calculating here in the plot, we have these equations. So the plots of the current I of t and the voltage across the resistor VR of t is called an exponential growth curves, and the voltage across the inductor VL of t is called an exponential decay curve, as you can see here. So this is for this today's video. Thank you.